like 15 minutes late, you know.
Okay, well, I guess let's start. So it's 7:30. We have 3 hours until the early part of the evening, and then we can potentially do more. So in this session, we'll be talking mostly about quantum error correction. We'll be using a lot of the vocabulary we built in the previous section on the stabilizer formalism. And I guess that deserves a little bit of a clarification here. Quantum error correction can refer to a couple of different interesting families of techniques, but we'll be focusing specifically on stabilizer codes. These are error correction codes that are very closely related to classical binary linear error correcting codes. These are probably the most important set of error correction tools we have, especially when we're talking about qubits and scalable computation. You might have also heard about bosonic error correction, where you're encoding a qubit into a harmonic oscillator. You might have heard about GKP codes, CAD codes, other bosonic codes. Those are interesting in their own right, but they're more of a technique to take a noisy quantum harmonic oscillator-like system and turn it into one or more reliable, somewhat reliable qubits. But on top of those qubits, you will again need to have these scalable stabilizer codes anyway. And whenever you hear an error correcting code, if there is no qualifier to that, they're probably talking about these stabilizer error correcting codes. And as the name suggests, they'll be very related to the stabilizer formalism. So for the first part today, I have this notebook that I've also shared on Zulip. It's a Jupyter notebook that also has embedded in it a slides-like formatting. It uses Rise, a plugin for Jupyter. If you like this type of stuff, you can even load it yourself as a presentation. I'll work through it first a little bit directly as code so that you can get the context of what's happening, but then I'll switch to using it mostly as a slide deck. And as you go through it, you can use it as a slide deck, you can use it as a notebook, you can go along and modify and execute the code as we're going through it, or you can just perceive the presentation. I like in this type of stuff to always have a package.status command to avoid issues like the issue on Tuesday where something slightly different was installed on your system than on mine, and you had a bug because we hit the 12-hour period when someone had merged something broken and no one had reported it yet. You can go to the Julia Slack to see that person being very sad about it. I have a couple of different packages I'll be using. Kairomaki, we will need it so that we can make some plots of the evaluation of our error correcting codes. Quantex is a small library for generating LaTeX TIGS drawings of quantum circuits. We don't really need it. You can just comment this out. Quantum Clifford is the same library we used last time in order to learn a little bit more about the stabilizer formalism. And its .ECC module has a bunch of interesting predefined codes, including some really advanced and sophisticated codes. And I have these time statements just because I'm generally interested in making things a little bit less latency bound in Julia, so I frequently just measure that. And last thing, I also have the version info because, again, it's informative if something's not working, so you know who has executed the notebook before you. Before we start, I'll just execute those two cells. It's just some plotting function that will be making pretty plots for our error correcting codes evaluations. It's not too important. But I'm executing it just so the presentation works, and I'm telling you that just in case you're working with a notebook as a notebook, not as just a presentation that you're going along with. Okay, so I will be using the Quantum Clifford library for a lot of the demos, but before we continue, I just want to mention other tools that you probably should be familiar with if you want to do a lot of error correcting work. Definitely STIM. It's an extremely important toolbox for simulating error correcting circuits. Quantum Clifford can do it. It uses the same algorithm. It has the same performance. It can do it even on a GPU, something that STIM cannot do. But STIM is just industry standards. If you're going to interact with other folks using such tools, if you're just going to evaluate results that someone else is giving you and you don't want to be the expert on error correcting codes, familiarity with STIM is the vocabulary that you need to talk to other folks in the field. There is TSIM, which is a bit of a joke on STIM, which is basically something like STIM, but capable of also simulating some non-Clifford gates for more advanced analysis of noise that cannot be represented as polynoise. We'll discuss these topics. And equivalently, almost the same tool, Clift, very similar to TSIM. Both of these tools were released in the last couple of months, one from the Inter Foundation and another one from Quera. Both of these tools are useful if you want to model something that's mostly Clifford circuits, plus a little bit of T-gates. Again, Quantum Clifford can do this as well, but it's useful for you to be able to choose your own tool as well, for you to judge what tool is best for your workflow and the environment that you prefer to work in. And as usual, my justification for using this tool, besides the fact that I'm involved in making it and I like it, is that in Julia, it's very easy to look at the source code and learn a little bit more about how it works. While these other tools are Python wrappers around something written in Rust or C++, it's much more difficult to hack around with it and to modify it. Okay, so with that out of the way, first thing we'll do today is focus on classical error correcting codes. And actually, before I continue, who here is familiar or has worked before with quantum error correcting codes?
Just okay. The word, I definitely know the word.
Okay. Well, so this hopefully will be a particularly helpful and useful session. Okay, so first thing, let's start with classical linear codes. Not all codes are linear, but we won't be going through what other codes might be like. The vast majority, by astronomical margin, any classical error correction is using this type of approach. And it's not particularly useful right now to discuss the edge cases that might be of theoretical interest. We'll start with something called the repetition code. And generally, the idea with these codes is that you'll be introducing some redundancy in the data you're trying to save or transmit, so that if something bad happens, the redundancy would be there to permit you to recover what was lost. So the repetition code is a very natural, simple code. The redundancy is just a little bit of repetition. The same way, if someone doesn't hear me, I just repeat myself and maybe say it twice or three times. That's what the repetition code is. So let's do it a little bit more formally, though. So we'll introduce the notion, two important notions here, parity-check matrix and a code word. So when we have a message we want to encode, for instance, the bit 0 is one possible message and the bit 1 is another possible message, we will introduce the notion of a code word where instead of sending the bit 1, we'll send the code word corresponding to the bit 1. And for a simple repetition code of 3 bits, that is just 1, 1, 1. And we'll write these down as binary vectors. So now the other thing I want to mention is that we would formalize the redundancy in a little bit more universal manner than just describing how something is repeated, because we would want to have codes that are not just strictly in terms of repetition. We'll be describing the redundancy in terms of some set of linear constraints that our code words have to obey. So instead of saying the repetition code is the code for which the logical bit I want to transmit, I just repeat it into multiple physical bits. I'll trace this differently. The repetition code is the code in which the code words need to obey the following constraints. And a parity-check matrix, like any matrix, is just a list of linear constraints. And let's read those constraints. The first row of the parity-check matrix is 1, 1, 0. It means that as a linear equation, the first variable multiplied by 1 plus the second variable multiplied by 1 plus the third variable multiplied by 0 has to be equal to 0. That's how you encode the linear equation in a matrix. Well, first, here, this linear equation will be a binary linear equation. So 1 plus 1 will be equal to 0 for us. And second, let's check that this code word actually obeys that constraint. The first variable times 1 plus the second variable times 1, that's 1 plus 1, plus the third variable times 0, so plus 0. So 1 plus 1 plus 0, that's equal to 0. Let's check that the other linear constraint is obeyed as well. This one says that the second variable plus the third variable has to be equal to 0. So indeed, that's the case. This variable plus this variable is equal to 0. So we use this description just because if we set it up like that, checking for errors becomes much simpler. We don't need to check the message that we received and compare it against every single possible code word, and we'll have exponentially many code words. We just compute the constraints and check whether the constraints are obeyed much faster. So we know how much easier to detect an error that way. Second, it's much easier to do encoding in this fashion. If we were to do encoding, if we didn't have this linear property, we'll need to store some exponentially large dictionary of input messages to output to encoded messages. Here, encoding is again just a linear operation where we get the input bit string, we multiply it, we get it as a binary vector, we multiply it by another linear operator, and the output would be the encoded code word. So now let's go through a couple of examples of actually trying to do error correction, to detect errors and to correct errors with this approach. And I'll try to, on one hand, do it hand-wavily to explain the intuition behind the repetition code, where there is this very natural idea of repetition. And on the other hand, I'll try to present this more abstract notion of error correcting, linear error correcting codes, where we have some notion of a parity check matrix and how we use that parity check matrix. The value being that the second approach is much more general and you can generate really interesting, weird, powerful error correcting codes if you use the second approach. So, oops, apologies. So as I mentioned, the code word C needs to obey the constraint that the parity check matrix H times the code word C is equal to 0. The code word needs to live in the kernel of the parity check matrix. And let's just check that that's true. It's the computation that we did manually, but we'll be doing all of these in code as well, just to build the habit of how you would implement something like this. And indeed, both of the constraints are obeyed. By the way, this vector, the vector of constraints, where 0 means that the constraint is obeyed, 1 means that the constraint is broken, this vector is called the syndrome. You have an error, you have a code word, you measure its parity checks, and then the result is the syndrome, because the syndrome shows you whether there is something bad happening, some sickness that you need to fix. So with that, let's start considering an error. We want to transmit this encoded word. We want to transmit the message 1. We encode it into the code word 111. We transmit it, but what happens? We have an error. The first bit is flipped. That's what this error vector here represents. A 1 at a given location corresponds to a bit flip. And how do we compute the resulting noisy message? Well, it's just the error vector, XOR the code word. This XOR is really nothing more than addition modulo 2. And This will be our noisy received message on the other side. And now we'll be checking its parity constraints, in its parity checks. The first parity check is broken, but the second parity check is not broken. So now that we know that some of the parity checks are broken, we'll try to deduce what was the error in order to fix it. I mean, at this point, we can just stop here and say, we detected an error. We're just throwing everything out and starting from scratch. That's a valid error detection procedure. We want to do more though. We want to do error correction. We'll need to figure out how do we fix it now that we know the syndrome. From the syndrome, we'll need to backtrack and deduce the error and then to perform the correction operation. So there is one pretty important piece of information here though. It would be really annoying if for every single possible code word and error combination, there's a different syndrome, and then there's a difficulty here in figuring out what the error is and what the code word is at the same time. The fact that we're using a linear code simplifies this drastically. There's a property that we'll go through right now that I want to stress it's an extremely important property. So let's just look at the expression parity check of the received noisy message. So E plus C is the received noisy message. Let's just expand it. And more importantly, let's just remember that H dot C is equal to 0 because the code word by definition is something that lives in the kernel of the parity check matrix. By definition, the syndrome of a code word should be the 0 vector because all parity checks are obeyed by a code word. So the important thing here is that this syndrome vector depends only on the error. And we'll be exploiting this a lot. I'll kind of also want to remark on why this is important. Why am I talking about classical error correcting codes? This particular property is incredibly important for quantum error correction. You know how if you have superposition, if you measure and learn something about the various options in the superposition, you lose information. So we need to figure out a measurement, a quantum measurement, that measures the message we received. It's incapable of learning something about the code word that was meant to be sent, but it is capable of learning something about the error that might have occurred. We don't want a measurement on our quantum code that learns about code words, because that means we cannot have superpositions between code words, which means that we cannot have quantum advantage. We want our measurement to be capable of detecting only things related to the error, not things related to the code word itself. And that's why this inspiration from classical error correcting codes is so important, because in this linear binary classical error correcting codes, the syndrome, the measurement result, depends only on the error. It does not depend on the code word. Yep.
So in this particular example, the syndrome is not unique, right?
That's another problem that we need to go through. Yes, it's the mapping is many to one. So, and actually that's the next topic. We now need to talk about error correction. And another term here is syndrome decoding. So when you talk about error correction, folks might say the word decoding to mean from a code word to get back to the original message. Especially in quantum error correction, the word decoding is frequently referring to from the syndrome deducing what the error was. So just mentioning that to avoid confusion. So the process of error correction is the process of mapping from the syndrome to the error that has caused the syndrome. And notice that many different errors can cause the same syndrome. So it's not like that mapping in reverse is easy to do. Notice also that from an error to syndrome, the computation is very trivial. It's just a matrix multiplication. The computation in the opposite direction, well, first, it's many to one, so one to many. You don't have a unique error that caused your syndrome. So at best, what you can hope for is to find the most probable error that gave you your syndrome. So in error correction, frequently you will not have perfect error correction. Rather, you have the error rate goes from 1% to 1 in a million. That's what we'll be doing. It will never be, unless you're in some thermodynamic limit, it will never be zero chance for an error. The error correction code will just drastically lower the chance for error. The issue is now, what would be the algorithm we use for this inverse mapping? Well, one simple option is to just build a large lookup table, start enumerating errors. That's easy. Sure, there's exponentially many of them, but enumerate the most probable ones, the ones with low weight. Compute the corresponding syndrome. That's easy. It's matrix multiplication. And store this in a dictionary and use it for lookup down the line. That's called a lookup-table decoder. It's a terrible decoder because it requires exponential amount of space for it to work well. In general, the decoding problem, unless you have some structure to exploit, is NP hard problem. It's a case of maximum likelihood estimation problem, where you have a situation where you want to estimate what is the error that had the maximum likelihood to have occurred conditioned on the syndrome that you have observed. And then for many codes, classical and quantum codes, they're interesting heuristics that work much more efficiently. In some situations that they're not only heuristics, they're provably efficient. And we'll go through those as well. But let's talk about how we will be making this lookup table. Let's start doing actually a few numerical experiments. Building a good decoder is a difficult task. It would be something where you have some algorithm to which you probably give something defining the code, something that tells the algorithm what would be the mapping from error to syndrome that to be trying to inverse, for instance, by giving it the parity-check matrix. Then it will be doing something with that parity-check matrix to prepare the decoder itself. Maybe it would be a machine learning one, maybe it would be a lookup table like this one, or maybe it would be some interesting graph algorithm. Those are particularly popular techniques. If you want to learn about more important decoding algorithms, I would suggest take a note to look into belief propagation decoding. This general class of algorithms that's pretty important, but we won't be going through them. Yep. It doesn't. That's the issue. Two errors might give you the same syndrome. You just put only the higher probability error in this table. That's it. That's the best you can do. Like this is not even a computational complexity statement. This is an information theoretical statement. You cannot do better than this. At best, you can deduce what's the most probable error, which leaves you with some smaller probability of error correcting incorrectly. And that's what we call inducing a logical error, because you thought that you did error correction and you did end up with a code word, but with the wrong code word. And maybe we'll go through an example of that. So let's make a really naive lookup table. Another question?
You said the syndrome is defined by just matrix vector multiplication, right? HE
Yeah.
S. Maybe this might be stupid, but why can't you do a pseudo inverse to go back?
Because, well, I'll answer a slightly different question first. You cannot do an inverse because the matrix is not square. It cannot be square because if it's a square matrix, you are not left with any logical bits. So say you have code words of length n, and you put C constraints. When you put the first constraint, you're left with one fewer degrees of freedom. So you have n minus one logical bits that you can store. If you have C constraints, you have n minus C logical bits you can store. So you don't want to have as many constraints as bits, because that will leave you with only one possible code word, so you cannot encode information. But you specifically set a pseudo-inverse. there are various techniques to 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 find an inverse of a mapping like this. The issue is that it's not easy, it's not cheap to have a pseudo inverse that gives you the most probable error. You will find some error, but it won't be the most probable error. So it won't be a useful correction. More of the time, it will be just leading to a logical error. It will be giving you a valid code word, but it won't be the code word that was most probably the one sent to you. So, and then the maximum likelihood estimator algorithm, that one is very much a pseudo inverse, but that one is an expensive algorithm because it gives you the most probable pseudo inverse. So let's do another form of such a inverting as such decoding, the lookup table. So I'm just preparing some dictionary. That will be my lookup table. I'm taking the dimensions of my matrix just so that I know what's the number of constraints, the number of rows in my matrix, and the number of bits in my code words, the number of columns in my matrix. I'll be initializing the lookup table with the simple case. If we have a zero syndrome, we know that we will have no error, most probably. And remember that I mentioned most probably. We'll get back to that. And then we'll start filling up this lookup table with errors. And here I won't generate every single possible error. I'll generate only single bit errors. Like 2 bits flipping is less probable than 1 bit flipping. 3 bits flipping is even less probable. So if we want to start filling up the table only with its most probable syndrome to error mappings, we should have the most probable errors in our generation. So for this case, I'm actually restricting myself very heavily to only single bit errors. I'm getting my error vector, just a vector of zeros. I'm picking a specific bit to be flipped and I'm marking it as 1. I'm computing the corresponding syndrome and I'm storing the inverse mapping in my lookup table. And that's it. That's one of the easiest decoder to write. In many situations, it is the best decoder to write if you know that you'll be working with a small number of logical bits. Query, for instance, right now for its Gemini machine that's being deployed in Japan is very much using lookup table decoders, but they're decoders that are guaranteed to not work well down the line, because if you have even a moderate number of qubits, well, this lookup table size grows exponentially in the number of qubits because the number of possible error words is exponential in the number of bits of that error word. But we'll be doing small experiments, so let's stick to this lookup table decoder for the moment. And let's build the lookup table decoder for this particular code. So I'm giving it the parity-check matrix we described earlier. And that's the lookup table. If we have both parity checks be fulfilled, there's no error. If both parity checks were broken, well, which bit affects both checks? It's the middle bit. If only the first parity check is broken, the first bit must be the one that was experiencing an error, and so on. But notice another thing. Maybe just on your own paper, I'm curious if the error was the following error. If the error was the first bit was not flipped, but both the second and third bit were flipped, what would be the syndrome we get from this error? A bunch of people said 1-0, and I frequently ask questions before having talked through the answers. So let's see. 0 flips, 1 flip. Well, 1 modulo 2 is 1. So yeah, the first check that checks whether those two guys are the same will be flipped. And the second check that checks whether those two guys are the same will not be flipped. So it will be this guy. And if we experience this error, our decoder will tell us that, and it will tell us this correctly, that most probably it was the first bit that was flipped. So we'll perform that correction. And overall, what is the total flipping that happened at the end? Every single bit was flipped. So we actually got the opposite of the message that was sent to us. The important thing is that if the error rates per qubit or per bit are independent, this error has probability p squared, while this error has probability p. And for a small p squared is much smaller than p. So this would be suppressing this decoder, this error creating code together with this decoder will be suppressing errors quadratically. It will be fixing the things that would have happened at probability p, but it will be leaving the things that would have happened at probability p squared. Yep.
Is majority rule the best we can do? Is there some more complicated?
For this one, majority rule is the best we can do. And I guess let's explain why we're talking about majority rule. For repetition code, the intuitive hand-wavy decoding rule is just check what most of the qubits are, and that's the most of the bits are, and that's the correct message. So this decoder is very much doing majority rule decoding. But majority rule decoding works only for, it's the best thing to do for the repetition code, but it also works only for the repetition code. We will be using codes where you cannot really, first, you'll be assigning more than one logical bit to your block of physical bits. And second, you won't really be distinguishing where a logical bit is. It's not like you have a bunch of physical bits and these physical bits correspond to one logical bit, and these physical bits correspond to one logical bit. Rather, all of your logical bits are uniformly distributed, quote unquote, over all your physical bits. Other questions? Well, let's run a quick experiment now. Pretty much any evaluation of the performance of error correcting codes will be based on Monte Carlo sampling. Theorists do prove really interesting things about the properties of codes, but those codes are frequently very useful constructions to prove that something is possible, but not the engineering constructions used in practice. For any practical error correcting code, this is very much how its quality is being evaluated with a Monte Carlo simulation where you randomly generate errors, you apply them to your system, and you see whether you were able to correct them. So for the repetition code, the curve that we'll be deriving, you can derive it theoretically. You can do that. We almost did that just now when I was talking about errors at rate p versus errors at rate p squared. But let's see what an evaluator for a decoder looks like. So we specify the code and we specify the decoder. We will be always evaluating code and decoder together. And we specify the error rate, the error model more generally, at which we'll be evaluating them, and the number of samples, I guess. So again, the number of constraints, the number of bits, and a count that tells us how many times did we successfully decode. And then we'll be just making a bunch of samples completely independently. This can be multi-threaded if you want. And for every single sample, first we'll be generating a random error. What am I doing here? I'm creating a vector of booleans where the probability for a boolean to be true is p. So this is my error vector where each qubit is flipped with an independent probability p. I'm calculating the syndrome. I'm guessing, I'm using the decoder to guess what is the most probable correction. And if the guess was correct, I'm increasing my counter. And yeah. Sorry, could you repeat that? Yeah, I guess if someone puts a p that's not between 0 and sorry. I got,
Because then the to flip will be higher.
yes. Sorry, apologies. I pressed the button and I really screwed up the presentation. So let me just get back to it.
What is this presentation environment, just for curiosity?
This is a Jupyter notebook using the standard Jupyter Lab plugin called Rise that lets you turn the Jupyter notebook into a presentation. Yeah. So let me just get back to where you were asking the question, and I'll be more careful with what buttons I'm pressing. So you were saying that I'm not checking whether P is valid, right? That's true. If someone uses this function and gives it a P that's not between 0 and 1, they'll get nonsensical results. So we have this evaluator, Monte Carlo evaluator ready. Let's run it now. For error rates from 1% to 50%, I'll be running the decoder, the evaluator of the code in the decoder for each one of these error rates, and I will use this list comprehension to store it in a vector. And I'll even count how long it takes. So it was pretty fast. And now I'm using that function that we defined at the very start of the class that I didn't want to bother with. It's just something that will be plotting the error rates in a nice plot. So what do we have here? We have the error rate that we put in, the probability for a given physical bit to be flipped. And here we have the probability for correcting for any possible flips that have happened. This line here, the black line, is the logical error rate equals physical error rate line. Sorry, it's not really rate, it's probability. And if the code is working, these dots that represent errors after decoding, these dots should be underneath the bisectress. This means that if we had an error rate of 0.2 for an unencoded message, the error rate, if we use the error correcting code, is closer to 0.1. Do you feel comfortable with what this plot is showing? Yep. Yes. So for every single one of these error rates, we ran the 10,000 samples and if counted how many of them we successfully decoded, and we're plotting this fraction, well, the fraction of not decoded ones here. Okay. Questions up to here. This plot is kind of important. We'll be looking at this type of plot a lot, so I'll stop for a second in case there's lack of clarity. This is probably one of the more important places to stop me to discuss if it's not clear what this is showing.
But is that a valid idea? Because like when you think about it, if the error rate is like very close to 0, if you wouldn't have errors, which means you wouldn't have correctly decoded values out of it. And I don't know how to put it. It's like, how do you know, it's like 1 minus decoded by sample space. If the error rate is close to 0, the decoded is very close to 0.
So I guess there are a couple of related things here. This type of plots, usually they'll be on a log-log axis. They're more informative that way because you kind of want to look at the slope of this curve on a log axis because that slope informs you about weights of errors that can be corrected, something called the distance of the code. We'll get to that, not too important. Second thing, if your error rate is very small, you will indeed need to sample in a smarter way. You either sample by making sure that you generate at least a single bit error and you kind of reweight, or you just run more samples. If you want to evaluate something at an error rate, at a logical error rate of epsilon, you better have 1 over epsilon squared samples. Because for a Monte Carlo sampling, your error rate is 1 over square root of the number of samples. you frequently actually very much will care about what's happening here very close to zero, because it's not like we will bother with a qubit that has a 50% chance for an error. That won't be a useful system. That would be just too prohibitive to work with. So usually we're pushing the hardware to have a native error rate of maybe 1 in 1,000. That's a reasonable goal. And then you're using the error correcting code to push the error rate to 1 in 1,000,000,000. As another example of error correcting codes, you're actually using error correcting codes in every single one of these laptops right now. The PCIe connection between the GPU and the CPU uses error correction. And what is the error rate of your CPUs? I mean, your CPU does like 1,000,000,000 operations a second. So your error rate is much lower than 1 in 1,000,000,000, because it's not like your computer makes a computational error every second. And that's what we want from a quantum computer too. The error rates that we actually care about would be on the order of 1 in 1,000,000,000,000. That's something that's necessary for reliable computation. And that's something that your computer does support for its PCIe bus between GPUs and CPUs. Okay, other questions? Well, yeah, we want the error rate to be small. We want this curve to drop down. We frequently, very frequently, we'll actually phrase it as the error rate for your physical bit, sorry, the error probability for a physical bit is P. What is the error probability for a logical bit? Frequently, it will be written as P to the power of something, that something being related to a figure of merit called distance, and you'd want this something to be very large. So useful today for codes that we're working with, the codes that are being deployed in actual hardware, the goal is usually to have a mapping from P to the power of 6. That's the hope.
Sorry, what was the name of the y-axis again?
Logical error rate, logical error probability, physical error probability.
So logical error probability is basically even after correcting, or in the process of correcting the error, did I actually incur the error? Right?
Yes, yes. So for instance, at this probability 0.2, there is some chance that you have 2 bits being flipped at the same time, and that is not something you'll be able to correct. So for the repetition code, deriving this curve is actually pretty easy, and that's a good exercise. Derive this curve theoretically. Yep.
I just happened to run this for P up till 0.8, and I saw that the after decoding error went up beyond the linear curve.
Yeah, at some point.
Is that just because we are missing errors in our naive lookup table that we?
No, it's just unsurmountable issue. This is called, so these two curves intersect here. And I kind of didn't bother plotting it further, but let's do what your friend just did. See how it goes above? So the error correcting code becomes actively useless here. This intersection point is called the pseudo-threshold. Whenever you hear about a company achieving sub-threshold behavior or something like that, it's they finally made their hardware good enough for an error correcting code to be useful as opposed to actively detrimental. Because if in this error correction setup, if you know that your error rate is bigger than 50%, well, this error correction setup will be actively flipping things for you. So any code will have something like this. For any code, there will be, if there's no pseudo threshold, the black dots will just always be above the solid line. Best case scenario, you have a pseudo threshold. And for many codes, the goal is to push the pseudo threshold as high as possible. You want both the slope of this curve and the intersection point to be favorable to you.
there some sort of conserved quantity here that has to do with like the area under the?
No,
dot?
no. For this particular one, maybe, but no, there isn't in general some useful feature like this.
And a possibility to use like different parity matrices so that we can have two lookup tables.
Yes, but that's concatenating multiple codes. That will still lead to having more constraints, so fewer logical bits at the end. It will be more overhead. You make it, you make the distance higher, the capability of error correction higher, but you will lower the amount of storage.
Since we know the probability of a single bit error, given for this specific tree length code word, we know that the probability the probability that the errors will be on 2 bits instead of just 1 bit or even on 3 bits.
Yep.
So using that probability, can we not tune our error correction procedure?
It won't be better than this one. In principle, yes. Knowing your error model in more details would make the decoder better. Many decoders take into account your best guess for what the error rates are, including potentially different error rates on different qubits. This is very much a thing. For this particular case, no, though. For this particular case, it won't work any better. Yep.
Say we added 2 more bits and had a 5
Yep.
repetition code. Would the intersection stay at 0.5? Would we start to see like a step function shape?
Yes, you'll start seeing something that kind of looks like a phase transition. This is very much you're going to the thermodynamic limit. You're increasing the number of atoms and you'll start seeing a sharp phase transition. That's very much a thing with error correcting codes.
But it will still be 0.5.
For this particular code, it will just be 0.5.
The fact that we are assuming 2-qubit or 3-qubit gate errors are just proportional to the powers of the probability of single-qubit errors.
I am assuming an independent error model. 20 years ago, even 10 years ago, a very common argument for why quantum computers will never work was that you cannot assume that error probabilities will be completely independent. Nature will find a reason to introduce a high weight correlated error. Doesn't seem to be an actual problem. And if it was an actual problem, why wasn't it an actual problem for classical error correction too?
So we don't see hardware actually showing that, like we are safe in terms of correlated errors.
I'm certain that there are examples of hardware that has this issue, but that adds actually more structure to your noise. So then again, you pre-train your decoder to know about this and you solve the problem.
Sorry, this is a follow-up from somebody else. You just said something about error correcting codes will use the best guess for a error rate in the
Yep.
direction. Isn't the error rate measurable? Why would you need to guess the error rate?
Yeah, that's what I meant. You calibrate, you measure the error rate. Your best guess for what's happening in the system right now, it might have drifted a little bit, but that best guess is informed by a measurement for a little while ago. Yep.
Is there a theoretical limit to the threshold or?
I don't know. Frequently, the threshold is more around 1% for practically useful codes. Yeah. Not 50% like here. Okay, well, let's continue. Okay, so we'll jump into quantum error correction now. And at some point, I'll talk a little bit more formally about it, but for the moment, we'll just do it rather hand-wavily. So this is the Steane code. This is the parity check matrix of the Steane code. It should look very familiar to something we saw in the session on the stabilizer formalism. So what do we have here? We have a bunch of poly measurements, and every single one of those poly measurements will correspond to enforcing a constraint on our system. And remember, when we're talking about stabilizer states, we said that if we have n qubits, we better have n constraints so that we fully define what our state is. Well, we just use the same logic here, but we remove some of the constraints. Then the Hilbert space the mutual eigenspace with eigenvalue plus one of all of these constraints, all of these stabilizers, will be not one-dimensional. It will be some dimension that's 2 to the power of something. That something will be the number of logical degrees of freedom, of logical qubits we have. So let's count here. We have 1, 2, 3, 4, 5, 6, 7 columns. We have 7 physical qubits. And we have 6 rows. So the Hilbert space that we're left with after we enforce that the eigenvalue for every single one of these measurements is plus 1, the Hilbert space will be of dimension 2 to the power 7 minus 6, 2 to the power of 1. Yep.
Should be a eigenstate of identity.
Sorry, could you repeat that?
The state is also an eigenstate of identity, I would assume. That doesn't count.
I'm not completely following. Could you elaborate?
Identity is also a polystring, right?
Yes, yes.
And the state is an eigenstate of identity string.
That's true, but I'm not bothering to write it down because any state would be an eigenstate with an eigenvalue plus 1 of the identity.
So when you say for each state, we need like n polystrings to determine it, that's excluding identity.
And independent polystrings. And polystrings that cannot be written down in terms of another polystring. An identity can be written down in terms of any other polystring. Just multiply that polystring by itself. Same reason when we talk about the zero vector, we say that it's linearly dependent on any other vector because just that other vector minus itself gives you the zero vector. So it's not a useful constraint. It doesn't provide you information that isn't already available from some other constraint. It's not a linearly independent constraint. And here we have linearly independent constraints under the idea of adding polystrings together in binary representation module 2. One way to say it is that the polystrings need to not be expressible as products of the other available polystrings. That's if we're talking about multiplication of polymatrices. But right now, when talking about error correction, it's much more convenient to say the polystrings need to be linearly independent from one another, where the addition operation is over their binary representation. Binary addition of polystrings is the same as multiplication of poly operators.
Semantic questions, probably. What is the definition of a code here?
A code is, so very hand-wavily, I actually like to say a code is just a parity check matrix, or in this case, a stabilizer tableau, a parity check tableau. So an error correcting code, more formally though, is a subspace of your Hilbert space. And what is the subspace here? It's the subspace of dimensionality 2 to the power of number of physical bits minus number of constraints. And that difference, physical bits minus number of constraints, is the number of logical bits. Actually, that's a good place to introduce some notation. Frequently for a classical code, you would write NK, the number of physical bits, the number of logical bits. For the repetition code, it would be 3, 1. For a quantum code, they use double brackets for whatever reason, and it's NK and D. D actually makes sense for classical codes too, but again, historical notation. So what is NK and D for this code? Well, we don't know what D is, so I'll just leave it as a question mark. We haven't defined it yet. N is 7, and K is 7 minus the number of constraints, 6 constraints, 1. We have only one logical bit here. Okay, other questions? Yep.
Is it usual for the number of logicals to be 2?
No, but the dimensionality of the Hilbert space in which your logical qubits live will be 2 because the dimension 2 to the some power, because qubits have 2 levels and tensor products of qubits will have 2 to the something. So it will always be 2 to the something, but the number of logical bits is the power. It's not the 2 to the something all together. And here, for instance, it's one. Sure, one is a power of two, but there are plenty of codes for which it's just some integer that's smaller than the number of physical bits.
I have a follow-up. So what is the thinking behind choosing these constraints?
This was one of the first codes that were discovered. And what was the logic here? Well, we need the checks to be commuting. That's one thing. And so that's probably, they have been thinking about that when they were picking this. The other thing is this happens to be two copies of the classical Hamming code. So someone knew about classical error correction and then tried to figure out a way to use a code to check for Z errors and a code to check for X errors. So these X measurements, they can detect Z errors being a phase flip. And these Z measurements, they can detect an X error being a bit flip. So these guys here is what will ensure that you can detect whether a qubit was flipped. And these guys here would be what ensures that you detect dephasing errors. So you need to detect not only bit flips, you need to detect something that's related to the phase of the superposition you're dealing with. These guys will be doing that for you.
And there's like some uniqueness property that it makes these parity constraints fixed.
Yes.
Okay.
But we can do change of basis. It's more of a canonicalization than anything else. There are other error correcting codes of this size. And in particular, we usually go to talk about codes that are like 100, 200 physical bits. And for those, there is an enormous variety of available codes. And you now are searching for a good code.
Thank you.
Yep.
So will decoding then, well, I guess not decoding in the sense that you're determining which error happened, but decoding in the sense that you're kind of rounding to the nearest code word. Would that be just
not nearest code word? That's important.
oh,
If we were looking for a code word, we would be destroying superposition. We won't be able to talk about superposition of code words. We're searching for the nearest error.
okay. So would that then be projection, just like this stabilizer tableau would define some subspace? Are we just projecting on?
Yeah, we are running every single one of these measurements. Our error detection procedure is to do this measurement, followed by this measurement, followed by this measurement, and so on. We do 6 measurements. And after we're done with the 6 measurements, we will be left with something that is a code word, something that is in the eigenspace, up to potentially having the wrong eigenvalue for one of these operators. And now we'll need to deduce what is the operation that brings us back into the code space. There will be many such operations. We will need to deduce the most probable one. But if you like classical error correction, you don't need to know anything about this. You can just look at this and think of it as 2 classical error correcting codes. One dealing with phase flips and one dealing with bit flips. And your whole simulation of its evaluation can be really 2 independent evaluations of 2 classical error correcting codes, where you happen to say that the bit flips in one of those codes are phase flips. You don't need to know quantum mechanics to model this thing.
Binary search that, like the first half of my qubits have a error, and then
For the Hamming code specifically, did you just notice that from the shape of it? Well, that was very impressive. You should feel pretty cool that you noticed that. I definitely didn't notice it until someone told me. For the Hamming code specifically, that is how the Hamming code was introduced. That is not how most advanced codes are made. But just because that regularity is oppressive, it has too much overhead. And you also want to be able to detect multi-qubit errors. This guy detects only single qubit errors. So there's a lot more randomness in the generation of a good classical or quantum code. But the early ones, the Hamming code was one of the earliest classical codes. This was one of the earliest quantum codes. The early ones really come from this type of logic that you just described. Okay. Yep.
The convention that the generator is only X and Z.
No, but it's much easier if that's the case. So when they're split like that, this is called a CSS code for Calderbank, Shor, and Steane, the same Steane. And the vast majority of codes being studied or deployed or used today are of this form. They're particularly convenient because a lot of infrastructure from classical decoding can be used. They're just easier to work with, easier to build. It's also known that they have a little bit extra overhead. But we're not at the point in the maturity of this technology to worry about this extra overhead. 20 years from now, all the standard codes in hardware probably will not be CSS codes. Every single code that is in vogue today is a CSS code.
What about continuous phase error?
There's nothing continuous here. We don't know about that. No bosonic error correction. We're sticking to qubits.
But I'm saying like phase flip is sure one.
Oh, that's yes. I'll just give, it's an interesting proof to show that. It's very well, very quickly, very briefly, and understandably shown in the Nielsen and Chuang textbook. But measuring these guys will decompose a continuous coherent or incoherent error, will decompose that error into a probabilistic polychannel. So the process of measuring these stabilizers turns a continuous error into a probabilistic mixture of poly errors. So that's it. And that I won't be talking about this at all anymore. If anything, the vast majority of modeling work happening at any company just doesn't bother with continuous errors because they do get projected into poly errors by the measurements, and you just do poly measurement simulation. If you have some special way to address continuous errors, you can do better than these codes. Not a low-hanging fruit, not something that's a priority for the industry right now, or academia. Okay. Yeah, you.
So just to confirm my understanding here, you said we apply each of these gates in succession.
No, we measure every single one of those
We
operators.
measure each one of these operators in succession, and we expect the measurement outcome to be positive one for each of them. And if we get a -1, that means there was an error somewhere. We can use that to.
Yeah, that's the syndrome. The syndrome vector is if you had a +1 eigenvalue, the syndrome vector is 0. If you had a -1 eigenvalue, the entry in the syndrome vector is 1.
That makes sense.
And frequently you actually will have two syndromes for the X checks and for the Z checks, and you decode them independently, and then you have some good enough performance based on purely classical error correction. And then you put them together and your performance will be slightly better because you get to deal with correlated errors better. Okay, and I'll continue with actually evaluating this. So let's make the lookup table. This time the code will be a stabilizer tableau. The constraints in the number of qubits are the number of constraints is the number of rows, the number of qubits is the number of columns. The lookup table has something that takes a syndrome vector and returns a poly operator, because our errors now are not binary vectors, our errors are poly operators. And again, we fill it up with a trivial one. If the syndrome vector is all zeros, the most probable thing is that the error was just the identity operation. And then again, we'll be doing only single flip qubits. And the code is self-explanatory. This happens to be API supported by Quantum Clifford. Other tools will have some slightly different names for these things. But for every single qubit that we'll be affecting, now we'll be affecting it with not just a bit flip, single X, but we'll be affecting it with a phase flip, single Z, or with a combination of a phase flip and a bit flip, a single Y. And that's our error, a given type, single X, Y, or Z, on so many qubits total, where this particular qubit is the one that's affected. And we calculate the syndrome by computing the commutation between the error and the operator we're measuring. If they commute, the error measurement, if they commute, the measurement is not capable of detecting that error. If they commute, the error just moves within the same eigenspace. If they don't commute, the error moves us from one eigenspace to the other eigenspace. So we check the commutation relationship check is the check for whether the measurement will be triggered. This returns a syndrome vector. So what does this com function do? For the very specific polystring error, it computes its commutation relationship with every single one of the rows of code. So if code has C rows for C number of constraints, syndrome will have C entries. It will be a binary vector of length C. And then we put it in the lookup table. This from the syndrome in the inverse mapping onto the error. And that's our lookup table. And yeah, that's the lookup table. And let's do this lookup table for the Steane code. The Steane code, 7 qubits. We're dealing only with single qubit errors. So, and there are 3 different types of single qubit errors. So 7 times 3 would be 21 entries in our table. And 22 because also we have the trivial entry. And let's look at this. So this is the syndrome vector. And let's see if the syndrome, if only the second to last entry was triggered, it must have been an X error on the 3rd qubit. Let me also show the Steane code somewhere around here so that we can compare. Code. Let's get this guy. Oh, I broke something. Okay, here I am. Oh, that's terrible. Let me go here.
Could reuse the same cell and do like on code scheme.
Yeah, but then that's a better idea. You're right. Give me a second to try to fix this. Okay, and let's get back to the same location. So we have the lookup table, and we have the Steane table. And I want to show the Steane table and the code. It prints it terribly. So I'll do this. I'll first print the code, and I'll also show the table. And okay, this is a bit more legible. So let's see. Let's just verify one of these to make sure that we're following what's happening. I'm curious about the case in which the syndrome is only the last two. The last two of the syndrome bits are flipped. So if for this guy to be, well, let's check. Let's just check that this is correct. I won't be trying to deduce it from scratch. If this is our error, the X checks inherently cannot detect it, so I'm not bothering with them. Those guys would be zeros if I have an X error. And then here, if the 3rd bit experiences an X error, it won't be detected by the first check, it will be detected by this check and it will be detected by this check. So this one seems correct. Okay. And here we'll be evaluating the quality of the decoder, not too different from what we already did. We'll sample, we'll create a random poly error of this probability. No phase just means that we're not randomizing its phase. That's not important. We're extracting the syndrome. We're guessing whether we're guessing what's the most pro one based on the lookup table. And if the guess was correct, we increase the number of decoded ones. And we'll be making the very same plot for error rates from 0 to 0.09. And that's it. The code works. It doesn't work with very high pseudo threshold, but it works. As long as your error rate is smaller than 0.05, it's a useful code. Well, somewhat useful code. Questions up to here? Yep.
Kind of curious, why is it shaped like that? Is that
It's a parabola. It's p to the p squared.
there seem to be some outliers?
Numerical noise. That's it. It's just going up and down a little bit, and I haven't been plotting error bars. Okay, so we have almost 2 hours, and there are a couple of different options we can do. We can introduce the surface code and try to understand it better. We can talk a little bit more about fast simulation of such problems and decoders. And we can talk about advanced codes that are of actual interest today, not just pedagogical codes like the surface code. Codes that are called QLDPC codes, quantum low density parity check codes. The question mainly is, do you want to lean into the numerical techniques you need to know in order to be able to evaluate the quality of a code, learning how to find its logical operators and so on, and learning there are some edge cases that we haven't discussed here that actually would make this type of evaluator wrong. We need to learn how to check whether a guess is correct. The guess can actually be different from the exact error and still correct it properly. There's a little bit of that there. So let's take a 5-minute break, and when you're back, have a opinion whether you want to do something that's more numerical or something that's more theory focused. And let's reconvene at 48 past the hour.
I guess I just thought of this now.
I'll just come over.
No.
Develop a package, check it out.
Yeah.
Somebody else is already.
The stabilizer space also are vector stabilizer.
First, I should start with that, then he said.
This one,
There are two subspaces usually for which are the logical
stabilizer.
Usually in this case, I
you come to such a block, but some dense makes it a block.
Yeah, exactly. You're saying that they're not getting used. That's why I was like, oh, I was
That is
yes, that if you know which are the two states, and those are the ones that
come on.
let's see variant by all the for example, by applying
So yeah, for example, this one already doesn't work because if I apply XX, this one becomes 1, 1, 1. So this one is not stabilized. So there are some states. So you have like 6.
Not for the surface code, yeah.
6 stabilizers.
Less than.
But space of 7 qubits. So there should be 2 states are invariant.
Fridays and we should be like,
They commute with each other. So everyone counts the space in 2. We start with 1 and 7, and you end up with 2 to the 1. There are 2 states that if you apply everything, they are like completely invariant. And then if you see that something is different, you know that something went wrong, and then you get the idea of you don't get the full error, but you get
because that one's not a.
It's known that if the code is not CSS, it's like
just like
it's known that here equivalent to constant factor, but that constant factor is a useful thing to get away.
Nothing like a big win.
Yeah.
It looked like never really gone too very good. Like I know there's going to be just an example of like the kind of I was like trying to remind myself of
When it was 2-1 and 1-0,
okay, that makes sense. I'm trying to think like if it's true, if there's like hardware.
I guess because
I'm more scared of
I don't know.
theory work that you need to do to figure out how to generate.
That's like.
I think it's WA solve. Whatever you have to solve.
I mean, one common example of CSS, and that was
Continuous stuff.
have a short random different circuit. Start with
hydrogen atom model, and it goes from 0 to 3.
That is an air example. That's not CSS.
Right.
Basically, just which of those and that will be
Here you have like 7.
I mean, I guess that's like, yeah, I mean,
So it can be like 7
Or is
squares.
it
So
true,
we
just
the
the-
idea that it's maybe 1
like
maybe
yeah.
to
So,
structure of the diagram. It's reasonably non-local has good properties. I don't know if you can mess up space.
Yeah, but you also need like
Do they have a name?
Yeah, I saw the guy doing it.
I do nothing about it.
And you restrict yourself to
the example of the reader
They're different things, though, right?
that's,
Because when he's talking about decoding here, it's this not
two-level
stabilized
system.
with the air, right?
Right.
So when you talk about it,
Same way after that.
So it's a bit tricky.
It's like you don't want to take across. You run something and then you think that okay, it has some like some boundaries. Something to go to a higher level.
I heard it from the
Exactly.
Talked about that code. What is this? It's like one like. What is that?
They work. Yeah, no, that's what
Somehow unsurprising.
It's like when I first learned that. Initial thoughts of, well, what if I single show.
I think that's like hardware.
You want to take it
I'll just definitely practice.
But I think it's just like just like I don't think they'll be like chasing it. Still running.
Okay, let's continue. Numerics or topological codes theory? Okay.
Yeah, for sure.
That's the scarier part. Now I need to say stuff and so on. Okay, so let's
We were flipping coins to see which one was one.
okay. Well, let's start with the surface code. So the rest of the story now. Yeah.
Just a quick question, before you were saying that like most people are doing the CSS codes, does anybody do 5-qubit code?
I'm sure that there are demos with 5-qubit codes and so on, but all the codes we discussed right now are bad. They're small. Actually, yeah, sure. We're talking about theory. Let's first start with talking about what's a good code. Okay, so first, there are three important figures of merit when we're talking about codes. There is N, there is K, and there is D. N is the number of physical qubits. That's the how many columns your tableau has. K is the number of logical qubits. So this would be the difference between the number of columns and the number of checks, the number of rows. And D is the largest, the smallest undetectable error will have weight D. So for our code, this would be N. This would be N minus K, and then D, the distance, so physical qubits, logical qubits, D, the distance is the weight, the number of non-identity operators in the smallest error that is not detectable. So something that your measurement operators all commute with. And obviously we want K to be large and D to be large. And until recently, we were facing this brick wall of K never being bigger than roughly square root of N, and D never being bigger than roughly square root of N, and actually even having very difficult time to get a situation in which they're both square root of N-ish. Only in the last 3 years, three papers on the same week on arXiv figured out a way to have K and D, which are linear as a function of N. That works only if N is like 2 to the 100. So it's not like it's practical, but just the theory proof that it exists was such a big deal. And there was a flood of discoveries after that result. And now we actually have so many interesting good codes. Like the last 3 years just brought so much, I don't know, hope that things can actually work out. It was really difficult to find a good error correcting code before these results from 2022 or 2023. Like that was last year, right? Question.
What was the name of the papers?
I'll send them on Zoom. And they're theory papers that are incredibly uninformative if you want a practical error correcting code. They're really fun if you like the notion of expander graphs and de-randomization and so on. But let's switch to the most important quantum error correcting code that we've had, the one that was discovered in 2001. A very bad error correcting code, but an error correcting code that taught us a ton. So let's talk about the Toric-Code. So let's draw a torus first. The next 30 minutes will be probably me just describing to you how someone figured out an interesting error correcting code, an interesting parity check tableau based on a lot of solid state physics intuition. So because it's solid state physics intuition, the qubits need to be in a lattice, and we'll be talking about the error correcting code that's kind of induced by doing something on that lattice. If you're taking notes, this can be the subsection on Toric-Code. So let's draw a torus. Is this visible well? Yeah, it's reasonable. Yep, I said torus. Doesn't this look like a torus?
Oh, I thought it was like a donut. That's what I was thinking.
It looks like a cup.
So 1, 2, 3, 4, 5.
And a
Oops.
card.
Let's make the torus of equal sides. So implicitly, I'm taking these sides and gluing them together. And then I have a cylinder, and I'm taking those two tops and gluing them together, and that makes it into a torus. Okay, and I'll just draw these lines to convey that there is some repetition here. So this line here is the same as this line. And this line here is the same as this line and this line. So this line, this line, this line, and this line are the same line. Okay, so now on this lattice, and again, this is just someone's really interesting, really creative construction for how to construct an interesting parity check matrix, parity check tableau. So on this lattice, I'll start placing qubits. There will be a qubit on each edge. And I won't bother drawing all of them. Also, let's give some sizes of this. Let's call this L, and this is also L. And these are our physical qubits. So my first question is, what is N in terms of L? Sorry?
-1.
Well, L is the length here, and I'm tiling the whole surface, so it will be squared in some way, and then there will be some prefactor. One way to do it is there are these horizontal ones. How many horizontal ones are there? There are L squared horizontal ones, and then how many vertical ones are there? Also L squared vertical ones. So hopefully I'm not misremembering that there are two L squared. Okay. And now what I'm going to do is I'll start introducing parity checks. I'll say that every single plaquette, every single square will be a check. It will be a Z check. And historically, and even today, it's really helpful to try to introduce some geometry into how checks are happening and so on. That's why these are called topological codes, because you're exploiting something about the surface of the topology of the surface. So what does it mean when I'm saying that every single square is a check? It's a check. It means that these three qubits that touch this square, they are going to, sorry, these 4 qubits that touch the square, they're going to be measured in the z basis. One of my operators is the tensor product of z on this qubit, z on this qubit, z on this qubit, and z on this qubit. So a weight for check, a check that involves 4 qubits. And how many such checks do we have? CZ, Z constraints. Constraints. We have L squared such checks, right? And then the next thing we are introducing is we're introducing the cross operators. These are the plaquette operators. Now we have the cross operators where every single vertex, which also touches on x cube on 4 qubits, every single vertex will be an x check. So an x check that involves this guy, this guy, this guy, and this guy. While the z check involved this guy, this guy, this guy, and this guy. Okay? So how many CX do we have, which are the X constraints? Also L squared.
-1.
Why? Well, here, actually, let's put it here. This X check, do I have a different color? So this guy here will be touching this guy, this guy, this guy, and this guy, which is the same as this guy. Oh, by the way, this guy is the same as this guy. And this guy is the same as this guy. It's a torus. Isn't it obviously a torus? So, so maybe you guys were skipping this one, but this one is the same as this one. And it involves this, 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 and this.
Shouldn't they be independent?
I was really hoping that I would have this trick question, but yeah, they need to be independent, yes. That was going to be a trick question in about 10 minutes. So yes, these are not independent. So the spiel I was going to do is that, okay, let's count what K is. K would be N minus the number of constraints. The number of constraints is L squared here, so naively K should be equal to 0. But as someone spoiled it for all of us, these are not independent. Why are they not independent? The X and Z stuff is definitely independent. You cannot get a Z out of multiplying X's. So we can just ask the question for only one of them. Why are these square checks not independent? If we pick a check, how can we express that check in terms of products of the other checks?
Like apply check to each square or each vertex, it will like flip all of it. So
yeah,
check, like each qubit is acted by 2 checks, so it's trivial if we like do all of them.
Yeah, I'll rephrase it slightly, or just say it more loudly. What is the product of all plaquette operators? So take this operator, 4-qubit operator, multiply it with this 4-qubit operator, and so on. Multiply all L squared qubit operators together. Every single one of those qubits will be then acted upon by 2 Z's. For instance, this qubit will be acted upon by this guy and by this guy. This qubit here will be acted upon by this guy and this guy, who is the same as this guy. So the product of all checks is the identity operation, which means that if we pick this check is equal to the product of all the other checks. And that's why if we're talking about independence, there is a -1 here. Because if we pick a check, that check can be expressed in terms of all the other checks. I'm not going to attempt to prove that it's exactly -1. It is exactly -1. Which means that K would be equal to 2. The tableau itself is not a particularly legible tableau because here you have this nice 2D structure of where your qubits are. You need to kind of enumerate them here. So this is the first row, then this is the first row of little columns, then this is the second row and so on. So if you're to write these checks as a tableau, the tableau would look something like each line will be of weight 4. Each line will have only 4 entries, but the 4 entries will be distributed in kind of weird diagonal staircase fashion. They're not obvious, and we won't actually be using the tableau directly. At least analytically, this tableau won't look pretty if we were to work with it. Okay, so questions up to here about why these things are true. So let's figure out what happens if an error occurs. So let's pick a qubit. Well, I'll continue making a few more dots. Okay. So let's pick a qubit and figure out an error that's occurring on that qubit. For instance, actually, depending on how you're taking your notes, I'll start just animating stuff on this. So you might want to make a bunch of copies. There's a question from over there.
Yeah, I was just wondering, is this in any way related to, or maybe the intuition is like of stabilizer formalism for cluster states, like how you correct errors, like if you measure X and you get 1 and then you know what the propagation
Generally
rules are.
speaking, yes, but I wouldn't. It's still related to the stabilizer formalism, but that's it. So I'll delete these guys just because I want to draw specific errors and specific stabilizers now. So let's do an error that occurs here. So on this guy, an X error happens on this guy. This X here corresponds to an error. This qubit was flipped. What checks touch this qubit? This qubit is touched by 2 X checks, this X check and this X check, and it's touched by 2 Z checks, this Z check and this Z check. Which of these 4 checks will be triggered? Which of these will lead to a syndrome bit that is not 0? Indeed, the 2 Z checks around it. So this guy will be triggered, and this guy will be triggered. So the experimentalist will see the green dots. The experimentalist doesn't know that the blue X has happened, but they measure all their stabilizers, and if only the blue X has happened, the only stabilizing operators that will be triggered will be these 2. So now that the experimentalist has done that, and they need to do the error correction step, what will they do? Basically, I'm asking you, how do you decode this stabilizer? What's the rule? What's the algorithm that you're following heuristically in order to, when you have 2 blips, to find what's the most probable error that caused those 2 blips?
So back to the next gate in between.
Yeah, you draw a line between them, and wherever it crosses your qubits is probably where something bad happened. Let me stress this a little bit more intensely. Let's say that the following 2 qubits experienced errors. This qubit experienced an error, and this qubit experienced an error. Both of them experienced an error, an X error. So what are the stabilizers that touch these guys? There are a bunch of X stabilizers that touch these guys. They won't be triggered because it's an X error. And there are a bunch of Z stabilizers that touch these guys. Which Z stabilizers will be triggered? Indeed, this one and this one will be triggered. But what about this guy? This guy touches two qubits that were flipped. But it touches two qubits, an even number of qubits that were flipped. So this guy won't be triggered. So the experimentalist just sees this, and they need to connect the line between them, and that's their decoding heuristic. And actually, this is really, really important. Really important realization that you can talk about chains of errors, and those chains of errors basically will create a particle-anti-particle pair of non-trivial stable syndrome measurements. And like solid-state physicists and so on, they love talking about how these are pairs that when you bring them together, they annihilate, and they talk about the statistical physics of these annihilations, and they derive things about the error cracking rate and so on. It is related to something about anyons because tangent, really an important tangent. If you make a hole here and you twist some things and you then move a syndrome an error around, and it kind of acts as the statistics of these errors become weird. But we don't have holes. We don't have holes. Yep.
Let's say you have like two tools that have an X error. And because of that, like you'll have 4 Z's that like it's triggered. So how will they draw the lines between these?
Well, let's make an example of this. I won't even say the following measurement was uncovered. I'm not even telling you what were the errors. We're just doing what the experimentalists will see. The whole point for this is that it works without us knowing where the errors are. So this guy is triggered, this guy is triggered, and this guy is triggered, and this guy is triggered. So what is the correct correction operation? We have definitely detected an error. The syndrome is non-trivial. We have detected only X errors. Great, there were no Z errors. Maybe the Z error rate is very small. Maybe we just have a lot of dephasing, a lot of bit flipping. And what would be your decoding heuristic now? How do you vote for me to connect things? The logic here should be that we connect it such that there are the fewest number of errors. We want the most probable error. The most probable error is the error that has the lowest weight. So you're suggesting connecting this guy and this guy. But these two and these two are the same distance. Why should I prefer these two over these two?
Because if you connect those two, then there's two.
Okay, yeah, if I connect those two, I need to have this long path through here, or maybe through here. So yeah, we just performed minimal weight perfect matching. So you have the graph of triggered locations. It's a fully connected graph where the weight of the connection is equal to the distance. And on that graph, you need to pair up edges of that graph such that the total distance of connections is minimized. So we want a perfect matching because everyone is paired up, and you want it to be minimal weight. We use the minimal weight perfect matching algorithm that thankfully exists, and it's the polynomial algorithm. And that's the decoding algorithm for the surface code. There are other more advanced, better decoding algorithms, but this one works pretty well. This one doesn't account for the fact that, well, this is one path that we can use, but we could have just as well use this path. So there's some multiplicity of paths, and both of those paths would actually have been a correct correction. There's something about the degeneracy of errors. I'm just throwing words at you so that you can look them up later. There are a few caveats to this minimum weight perfect matching, but it's generally speaking a really good decoding algorithm for the surface code. Okay. Questions up to here?
Sorry, I think I missed the crucial point. Can you sort of remind me what exactly a path means here?
A path is if you have things that are triggered, like these two things. Sorry, let me rephrase. Something that's triggered because of the nature of the topology of the surface code. A triggered syndrome has to be the endpoint of a path of errors. We know that it has to be the case. If you have a syndrome that was triggered, there will be a syndrome bit that was triggered. There will be another bit that it's paired up with. So, the decoding process will be to find the most probable paths that are connecting those syndromes. And by path, I mean a sequence of neighboring qubits that are connecting them.
Right.
Yep.
What if all the 4 green dots are like adjacent in square or something?
Like
Doesn't matter.
it thankfully doesn't matter. We haven't encountered white though. So say this is what you have. Say this is what you have. And you can connect them like this, or you can connect them like this. If you connect them correctly, great. You cancel everything out. If you correct them incorrectly, you have introduced newer flips, but importantly, the overall set of flips will be a closed path. And a closed path that doesn't wrap around the torus is equivalent to the identity operation. It doesn't change your code word. Let's see, do I have a way to explain why?
So here, same weight, right?
Yeah. So connecting them like this, so let me erase the path I drew.
Doesn't our code have a huge possibility of not running?
Sorry, could you repeat that?
Our code has a high probability of not running. Said that we assume the code can correct the most probable one.
Yep.
But here there are 2.
Indeed. And they're equal probability, and that sounds really scary. It turns out that they're what is called degenerate. So say the actual thing that happened was an X error here and an X error here. This is the actual thing that happened. 50% probability, you corrected the proper way and you actually correct these X's. But 50% probability, you pick the wrong one and you do these guys instead. So now you have introduced extra flips. But for the moment, just take it as granted. I won't attempt to explain it yet. A closed loop for the Toric-Code, a closed loop of poly operator for the Toric-Code acts as the identity operation on the code subspace. So while this physically is indeed the tensor product of 4 x's, and this is physically an operation that will be doing something, it's not the identity operation. If you restrict that operation to the code subspace, it is the identity operation. This is not an obvious statement, but for the moment, just take it as granted. And that's one reason people like the Toric-Code, because studying this type of degenerate errors turns from a very difficult exercise related to the stabilizer tableau to a very pleasant kindergarten exercises of drawing closed loops. A contractible loop, although it is very much actual operations that are happening, when restricted to the code space, it acts as identity. A loop that's not contractible, it doesn't act as identity. A loop that's not contractible is an actual error. So while this degeneracy is fine, let me write down a different type of degeneracy that's actually very dangerous. Okay, the lattice size is not very convenient for this exercise, but let me just draw it like this. You have this guy here, and first, I'll just draw this guy here. So it's even simpler case of the previous issue we encountered. This path is equally valid to this path. But these paths are equivalent because you can switch from one to the other continuously without making a circle around the torus. This path is equal to this path times a closed circle. So because they're equivalent to each other up to a closed circle, they're performing the same correction. Same logic as the previous example that you guys set up for me. But what I want to discuss is actually this case here, where we have one option is this path straight through the torus, and another option is going around the torus. And those are of equal length. Which we go, if this is the torus and our flips are on both sides of the torus, we can go this way or we can go this way. These are much more dangerous type of ambiguities because now these two paths are not equivalent up to a continuous deformation. These two paths are they're equal to, if you multiply them together, you get a path that goes around the torus. And this is not acting as identity when restricted to the code space. And again, let's just take that part for granted for the moment. Let's not try to derive it. There's a question?
Yeah. So right now, k equals to 2 means there are like two more Pauli operations. If which we include, then the final space will be reduced to just like we fully specify the group, I guess.
It's exactly these two operations that I'm describing right now. The one possible circle around the torus. So let me draw the torus in a kindergarten fashion. So that's difficult. So does this look like a torus?
Yeah.
That was really difficult. Well, now I feel patronized. What are those two operators? And again, we actually need to only worry about operators up to contractible circles. Well, those two operators that are accounting for this difference that we need to specify in order to have a completely specified state, it is a sequence of operators around here and a sequence. So I guess this actually needs to be dashed. So one uncontractible loop and an uncontractible loop that's not equivalent to this one. So this loop won't work because this loop is equivalent to this one. But this loop works fine because this is also not a contractible loop, but it's not equivalent to this other contractible loop. So what do they look like here? It's a line going like this and a line going like this. Those are loops, and they're uncontractible loops. And they're the missing degrees of freedom that if we specify, we don't have a code space left. And they're very much related to the fact that we have this ambiguity that actually starts to matter here. Because if say the actual errors were going through here, and we decide to decode by doing error corrections around here, well, that creates a closed loop that's not contractible. That now it induces an error. This is not acting as the identity operation over the code space anymore. And that lets us calculate what D is. D is the smallest error, it's the smallest weight of an error that we cannot we cannot detect. I like the other definition. G over 2 is the smallest error that we cannot correct. So what's the smallest number of physical qubits that need to be triggered for us to have this ambiguity appear? These guys need to be far enough apart for there to be ambiguity. They need to be on opposite end of the torus for there to be ambiguity. They need to be L over 2 apart. So D is equal to L over 2 . Which more importantly, I will write it down as square root of n. So is this a good code? K is 2. No matter how large the torus is, K is always 2. That's ridiculous level of overhead in terms of encoding. And D, it's just square root of n. It's not even linear. So this is terrible and this is not okay. Up until 2023, we didn't have any examples where we had K being on the order of O of n and G being on the order of O of n. This was achieved in 2022 or 2023. And again, achieved only if n is like 2 to the 100. But these days, we actually do have solutions for good codes.
Yeah, so I think an assumption under all these is that our measurements are 100% accurate, right? Like
yes, so we're talking about something that people call error correction. We're not going into what people call fault tolerance. There are two things that we're missing here. What do we do to deal with the fact that measurements are imperfect? And what do we do to not just store quantum data, but perform quantum gates? There are two papers that I think are really good introduction to how to do that. Game of surface code. Skip the paper, just look at the YouTube talk. It's really, really, really high quality. And then something called poly-based computing. I don't have a really good canonical textbook paper for it, but there are some not bad ones. And those introduce the notion of fault tolerance. I will not be attempting to go into that, but it's really fun. Like you get two surface codes, you slam them together, you measure the stuff in between them, and then you rip them apart, and this magically performs the signal gate between the logical qubits. It's really fun stuff. Game of surface codes. And you can imagine when that paper was published. Before the last season was out. Okay, question?
Yeah, if four such errors happen, right, forming a square, which you said basically forms a closed loop, not just square.
Yep.
Such an operation, if neither the Z, the bucket, or the cross operations cannot detect that, and it is not one of these operations, that basically means the such error is nothing but product of these stabilizers that we already have, right? They are not unique in the group element. They are just the products of.
That's very much how you get to that point. And if you want to computationally do that in the Quantum Clifford library, and for this one, I do claim that the Julia library is probably the most convenient one. The other libraries are really good for circuit simulation, but they're very painful to get algebraic properties out. Take the mixed destabilizer object. Mixed destabilizer. And that constructor can take a stabilizer and give you the, well, it will give you the missing K terms. It can compute them for you. And it's not like you shouldn't try to learn how to do it on your own, but it's just some annoying Gaussian elimination procedure. It really helps when you're trying to study it. This object, with it acting on a parity-check matrix, you can get the other terms, the logical operators. Okay, so we have another hour, and I mean, we'll continue until after midnight if you want. Yeah.
Real quick question. So here we have K equals 2. And it appears to be that's because we have 2.
Yes, if you make more punctures, you can get better K.
So if you had m homotopy classes here, you would have n minus 1.
I don't know the exact relationship, but it's something like that. But be careful, if you puncture more holes, the smallest loop that you need to make in order to go around the hole will be smaller. So when you increase K, you diminish D. And there's actually a theorem that 2D topologies, no matter the holes, no matter the weirdness of the shape on which they're a surface of, a 2D surface cannot be a good code. A 2D surface will always obey some very, very constraining, very unpleasant relationship about K and D. I've never really learned how that's proven. That can be a fun homework. Okay. Sorry, could you repeat that? It involves something called expander graphs, which are graphs that are very sparse but very well connected. For mathematicians, the existence of such graphs initially was very much a surprise. Like, if a graph is sparse, how can it be well connected? Well connected being that there's always a short path between two locations. But any random graph has a very high probability of being an expander graph. So expander graphs are actually a really big deal in math. They're a really fun thing that was surprising that it exists. Now it's a really big deal in de-randomization. I mean, it has been a really big deal for decades. And so that's one of the components. You need expander graphs, whatever they are. You need something called Tanner codes, which is a standard way to build a parity-check matrix out of a graph. And I'll put links to those as well. Okay, so next thing, I can run you through kind of a high-level presentation. It's really just a slide deck on how to generalize this to good codes, the ideas that are necessary, the type of mathematics that are involved in it. Or we can talk more about how to extract logical operators, which is basically some more linear algebra. Or we can go back to numerics. I personally think that the slide deck on more advanced codes is biggest bang for the buck. On the other hand, it will be the one where you need to do the most just trust me, bro, because I won't be explaining or proving things. Any preferences?
We trust you, Stefan.
Okay.
Yeah, exactly. I feel like we're already high up there.
Can I just muting error corrections and are the bottleneck of quantum?
I mean, I work on that, so I will say that. I really think that a lot of hardware developers over the last decade were expecting that they would achieve what they achieved. Like error rates did go down, scale went up, things improved the way people that know how to build hardware expected. I don't think there is as of a universal expectation that there will be such monumental progress in error correction. I cannot stress how amazing the progress of the last 4 years has been. Like the expectation in terms of overhead, how many physical qubits you need to run an algorithm have dropped by so many orders of magnitude because of advancements related to error correcting codes. I am not the type of person that really knows how to construct the new advanced error correcting code. I'm doing more resource estimation type of work, modeling, trying to do more architecture type questions. But the people that figured out these new codes, they did achieve some pretty big leaps of creativity that to me were very non-obvious. Okay. So this is a slide deck I used a few weeks ago for a workshop. It's about the work that was done in my group. A student had a really nice construction for a particular set of codes. The specifics of that work don't matter too much for the purposes of this presentation, but the intro to it does cover a lot of important constructions, and those are the constructions that kind of are used fairly universally. So that would be the focus of that presentation. So the fact that it's multivariate, multi-cycle code doesn't matter too much, but we'll be talking about something called chain complexes. And those things are used all over the place to define these new, modern, interesting quantum error correcting codes. Okay, so we were talking about good codes, and good codes have a good distance, a good rate, and a good decoder. You do need to have a decoding algorithm that works well for them. So what does it mean for there to be a good rate? As n grows for a family of codes, we're frequently talking about a family of codes parameterized by the block size n, the block size being the number of physical qubits. The rate should not be vanishing. The limit should be going to a constant. The distance, same thing, the relative distance over n should be going to a constant. For the Toric-Code, we had 2 over n for the rate, and we had square root of n over n for the distance. Both of these are vanishing. Instead, we want what we call constant rate and constant distance. And we also want a good decoding algorithm to exist. In general, we don't want to use an exponential large lookup table. We need a decoding algorithm. The surface code did have a good decoding algorithm, the mean weight perfect matching decoder. And for classical codes, it's very easy to get a good classical code. You just make a big sparse random matrix that's not square. By picking the ratio of rows to columns, you're fixing the rate. And you just want the matrix to be sparse. And that, with very high probability, will be a good classical error correcting code. It's easy to decode because of its sparsity, the relationship between checks and bits that were flipped is relatively simple. You don't have a bit that might affect way too many checks or a check that might affect way too many bits. So various belief propagation algorithms work well. The formal way to say that is because locally the graph of checks and bits is tree-like, you have good convergence of decoding algorithm heuristics. This again relates to the fact that expander graphs exist. So I'll send some materials on that. I'm again sharing a few terms that it should be useful for you to know about. You don't really need to understand the proof behind why these statements are true right now. But it is true that a large sparse matrix is a good classical error correcting code. Your fonts are using error correcting codes to communicate to Wi-Fi and a different standard of codes to communicate to cell towers. That's how these were made. Someone just was running random matrices with maybe a little bit more structure and was doing tests on them, and then those were submitted to a standards body, and those were encoded in the standards as the error correcting codes that will be used. And it really started with more or less that line of Julia or MATLAB. For a quantum code, you need two classical codes. We kind of saw that with the CSS codes. There's a more general construction, but let's stick to just CSS codes. And their constraint, though, you need checks that commute. You cannot have the X checks and the Z checks to not commute with each other. So you're not permitted to have any two classical codes. You need two related classical codes. And this is the relationship that they need to obey. The parity-check matrix for X, then its dot product with the transpose of the parity-check matrix for Z has to be equal to 0, modulo 2, because this is binary multiplication. Why is this true? Because we want the X checks and the Z checks to match up in even number of locations. That's all this matrix equation says. Each X check and each Z check should overlap in exactly even number of spots. That's what this equation is saying. The issue now is that if you pick a good classical code for X randomly, which is very easy, it's very difficult to find a corresponding Z that's also just a sparse matrix. The naive ways to do that with some form of Gaussian elimination will lead to a dense matrix for the other code. And that won't lead to a good code. So you can have very easily a quantum error correcting code that protects well against X errors or against Z errors, but it's really difficult to just randomly sample for a good classical error correcting code that, quantum error correcting code that checks well for both X and Z. So yeah, sample a good PZ, find the compatible PX, and PX will be a bad code. So what we need is some form of a better representation, a better ensemble from which to sample, a better way to encode an error correcting code. We don't encode it as a parity check matrix. We find some other algebraic object that is, again, equivalent to the notion of an error correcting code, but it's easier to sample from. We want to find a data structure, a mathematical object that has these nice sparsity properties inherent to that class of objects, and we'll be sampling from this new class of objects. And again, it will be random sampling, but it will be a random sampling that somehow enforces that both the X and Z parts will be sparse. And there are two ways that have been becoming pretty common these days. The expander graphs approach, which is the one I mentioned a few times, the initial papers from 2023 or 22, again, I don't remember. And those are using the notion of expander graphs. They are interesting, but I won't be talking about them because they're frequently the less practical one, even though they're better for proving theorems. The one I'll be talking about is the one based around the notion of chain complexes. Pretty much any paper on quantum LDPC codes these days talks about chain complexes. The point of this slide deck is really just to explain what a chain complex is so that you have the vocabulary to read such a paper. So, a chain complex is used for many things, but among them, it's something you can use to describe quantum codes. So a chain complex is usually written like this. It's 3 letters that correspond to vector spaces with maps that map between the vector spaces. And what makes this special is that the maps have to be constrained to obey this property. And we'll see that this actually geometrically corresponds to something interesting related to the surface code, But when you write it like this, you throw away all the geometry and you just retain the important algebraic properties. And we'll be searching the mathematical literature from the last 3 decades for examples of these objects that encode all the properties we care about, all the properties we notice as important from the surface code, but without restricting us to something that has a nice geometric interpretation. And so without restricting us to this 2D case that enforces low rates and low distances. But for the moment, again, this is just a definition. What is a chain complex? It's a chain of vector spaces. These will be binary vector spaces. And the chain specifies the some specific maps between those vector spaces. They're not isomorphisms, they're just some maps, linear maps. And they have the properties that when you chain 2 of those maps together, they're equal to 0. So the product of the matrices representing those maps will be the 0 matrix. So why do mathematicians care about chain complexes, about this object? This object appears in an enormous amount of physics and mathematics. And we'll just go through a couple of examples that justify that mathematicians were right to start abstracting this away. And we'll see how this applies to electromagnetism as a tool to study electromagnetism. And I'm picking electromagnetism because I assume a lot of you are physicists and have studied electromagnetism. But then we'll see that they actually end up being extremely useful when constructing codes as well. Okay, so the chain complex is generally studied in the field of homological algebra, and kind of the motto of homological algebra is that the boundaries don't have a boundary. What does that motto mean? Well, homological algebra is really the way my friend in the math department described it is the study of linear algebra on spaces that have holes. On a torus, for instance, because it has holes. And it's a tool that's used a lot when studying when really studying anything related to topology, to how many holes exist, how many contractible circuits exist, what are the overall properties of an object without concerning yourself too much with its local properties. What can you say about its topology? And where does the motto come from about boundaries have no boundary? Let's just go through a couple of definitions that make this motto a little bit more intuitive. So first thing, take a filled-in circle on the sphere, like a black circle. What is the boundary of that circle? The boundary of the circle is the periphery. It's the circle as a line without a filling. Let's take another example. Take a line. What's the boundary of the line? It's the 2 end spots on the line. And third example. Take the boundary of the filled-in circle. So the boundary of the filled-in circle is just the periphery. And what's the boundary of the periphery? I mean, it doesn't have a start or an end. It's like when you took the line segment and connected it. It doesn't have a boundary anymore. There is nowhere where it stops or where it starts. That's the spirit of this motto. And right now it sounds silly, but we'll see shortly with the surface code that talking about the boundary of a boundary was actually pretty important. So for the moment, I'm just really trying to introduce vocabulary, nothing more than that. Any questions about the vocabulary? And this vocabulary is very hand-wavy. It's not like I'm trying to prove anything, but do you understand the concept of why I'm saying the boundary of the filled-in circle is the empty set? Okay. So let's talk about an example of a chain complex that you actually are probably very familiar with. And abuse of notation, there is something called a cochain complex. I barely understand the distinction. Let's not try to go through that distinction. Yeah.
So a cube, boundary of the cube is a surface.
Yeah.
But like in that sense, is the boundary.
Well, if you're talking about topology, there is no difference between a cube and a ball because, yeah. Like the fact that you've pinched the bow and made it sharp in one spot doesn't change anything about its topology. And that's where this type of study has been very useful. Like anything about, are you able to twist or turn this 3D surface and flatten it somewhere, or a continuous function on a sphere that needs to have you can prove that there will be a diameter where that continuous function is the same on one and other side. Like anything about antipodal equalities. This type of algebra is used to generalize the proofs for this type of problems. Like you might have heard that temperature is a continuous field, and you can prove that there are 2 points on Earth that are diametrically opposed that are at the exact same temperature, mathematically. It's not a question about physics. If you assume that temperature is a continuous function on a 2D surface of the 3D ball. Homological algebra is how you prove this, because it's something about how you will be twisting and turning that 2D surface until you flatten it in some way in which this equivalence is enforced. So that's why mathematicians started studying this field. 3 Blue 1 Brown has a nice video on that particular, any topology video from 3D 1 Brown, 3 Blue 1 Brown ends with a mention of, yeah, this is kind of like an intro to homological algebra. Okay, so let's go through an example of a chain complex you know of. So we start with the vector, with the vector space of scalar fields. This is a well-defined vector space. You have addition between scalar fields, and then there's a related field, a field of vector, a related vector space, the vector space of vector fields. And you have a map that takes, for any scalar field, it will give you a vector field. This is a map from the vector space of scalar fields to the vector space of vector fields. And you have a map from vector fields to other vector fields. I call them axial vector fields. If you know the term axial, great. If not, doesn't matter. But it's kind of like the map that starts from electric fields and ends with magnetic fields. Yep.
Is that, are you referring to like pseudo vectors? Or
yes, pseudo vectors.
Okay.
Axial vectors is what I call pseudo vectors. Maybe it's because I learned about them in France. I can swear that in France they call them axial vectors. I hope I'm not misremembering that. And notice you should remember from your multivariable calculus class that the curl of a gradient is 0, and that the divergence of a curl is also 0 if you want to go from an axial vector field to a scalar field. You use the divergence. Yep.
Is this also assuming something about the space we're in? Like,
yeah, it is assuming that it's a continuous, it assumes that it doesn't have holes, like no AB effect, Aharonov-Bohm effect, none of this here. But yeah, and again, by the way, studying that effect in terms of homological algebra seems to simplify things drastically. To mathematicians that know homological algebra, that effect doesn't look as weird as it looks to physicists. But my point of showing you this is that you're already very familiar with one very commonly used chain complex, the chain complex of fields related to electromagnetism. And for a mathematician, this succinct description immediately tells them so much about it that we, the physicists, had to learn in a whole series of graduate classes. It's really nice way to encode a ton of important properties. And I want to introduce another example of a chain complex. Remember how we had a chain of errors in the surface code, and then the ends of those chains were our syndrome bits? If you write down the vector space of errors, and you take a vector from the vector space of errors, and you apply to it the parity check matrix, you end up in a different vector space, the vector space of syndromes. So any syndrome is a boundary of an error. And for at least for the surface code, that's kind of obvious and pretty and elegant, because in that case, the boundary actually sounds like what we geometrically think of a boundary. The surface code is where this kind of becomes obvious. So the main point is, remember when we were drawing the chain of errors, and how for a chain of errors, the non-trivial syndrome bits were at the end of that chain. That's all this statement here is saying. Let's take this, let's think of it more abstractly, and let's just ask a mathematician, hey, I have this two-dimensional space in which I have this nice notion of the boundary of my errors is what I call my syndrome. But I have already proven that if I restrict myself to this 2D notion, I cannot achieve good rates and good distances. You, my math friend, could you generalize the notion of a syndrome being the boundary of an error to some space that doesn't have this 2D constraint? That probably would be extremely useful for me, because then I will use all of the machinery I have created in terms of boundaries and geometry and so on for the surface code. And everything that worked for the surface code now will work for this more general code. All I need to do is just blindly believe that what I call a boundary map is still a boundary map. I just preserve the algebraic properties I cared about, and I forget about the 2D topology that made it easy for me to derive these algebraic properties. You just give me some other object in which these algebraic properties are still fulfilled, even if they don't have this visual graphical representation anymore. That's why we're using chain complexes in quantum error correction, because a ton of the algebraic machinery that was devised for surface codes, machinery that was figured out because we had graphical representation of a 2D surface, we just take the algebraic properties and we generalize them, while losing the thing that permitted us to have this graphical understanding. It's the 2D nature that both constrained the capabilities of those codes to not be good rate and good distance, but they were what permitted us to derive the algebraic properties that led us to figure out how fault tolerance works. So keep the algebraic properties while dropping the 2D capabilities of them. Okay? That is a very abstract statement. It's not, it's more a statement of the spirit of why people started talking about these objects, because they still can talk about boundary without having that boundary be something that they can draw on a 2D surface. They still use the same words, even if they don't have geometric meaning anymore. But they keep the same algebraic properties, which is how they find something interesting. So how uncomfortable are you with continuing with this spirit? Okay, reasonably uncomfortable. Well, if we're going to do that, well, let's just ask our math friends about some good chain complexes.
Sorry, so the mappings are the boundaries then?
Sorry, could you repeat?
Is the mapping the boundary then?
Yeah, this little delta is the boundary.
Okay, cool.
It's the boundary map. So the error is the thing of which you're searching for the boundary, and the delta is the operation that takes the thing and finds its boundary. So every single arrow is a boundary map that takes something from the input vector space and it finds its boundary. So the error is the input thing. The arrow, this delta, is the boundary map that takes the input and finds the boundary of that input. the boundary lives in the different space, in the vector space of boundaries.
Just taking this idea directly to 3D make our D more efficient.
We're completely dropping the idea of a well-defined spatial dimension. Like it's all-to-all connectivity and so on is fine here. We don't have a geometric topology left anymore after we start taking this seriously.
Oh.
So let's talk about the quantum code. A quantum code is nothing more than two maps that have very special property, that one map times the transpose of the other map is equal to 0. So we can say that this actually is equivalent to a chain complex. We have one space in which the qubits live, in which the error vectors live. And there is a boundary map that for a given error vector will give us X checks, the X syndrome, and another boundary map, the transpose of this boundary map, that gives us the Z checks. And we just take into account the transpose so that we can write it as a chain complex. And that's it. This is where the error vectors live. This is where the syndromes live. This is where the other syndromes live. And now, in order to find a good error correcting code, we just ask our math friend, hey, could you give me a table of known constructions for length tree chain complexes over binary fields? And that's it. They give us something from 30 years ago where someone has figured out for some reason, some way to generate some such complexes. We pick one at random, and it's actually usually a pretty good code. And it gives us picking a way to sample from chain complexes gives us for free the constraint that we need, the constraint that X and Z checks commute. So now the question is, what is a common way to generate chain complexes over binary fields? Let me see where this presentation goes. This is just a reminder, the fact that the two parity checks, the X and Z parity checks have to commute. This is mathematically in the same spirit in which the divergence of a curve is 0. It's the same mathematical machinery that we're using to study these objects. So just a second. I'll skip a few things. So yeah, now at the end, we need a technique to find these sufficiently long chain complexes. We've actually already discussed at the very beginning of this slide deck a technique to find a good chain complex of length 2, a chain complex that has only one boundary map, a chain complex that corresponds to a classical code. So what a lot of quantum information science researchers discovered over the last 3 years is that there is a large amount of techniques that take short chain complexes and create longer chain complexes. So many works on modern quantum LDPC codes are nothing more than using some standard known approach for taking a few short chain complexes and making a longer chain complex. You remember that at the very beginning, I actually gave you such a technique. It was just a very bad technique. It was kind of an obvious technique for us. It was the technique where we start with one good classical code, and we do some Gaussian elimination to find the corresponding classical code for the X checks. That is very much a technique that takes a short chain complex and it makes a longer chain complex. It's just a bad technique that doesn't result into a sparse, nice boundary map for the longer chain complex. Instead of starting with a chain complex and just trying to make it longer, what mathematicians provide us with is a technique that starts with multiple different chain complexes that are short, And they have defined the notion of a product of chain complexes that takes two short chain complexes and makes a new chain complex that's much longer. And that's all we want, really. All we need here is to pick a few good short chain complexes that we know how to do. We just pick big random matrices. And we use one of these standard techniques that takes two independent ones and makes one longer one. It's not like it chains them together. That's difficult. But it takes two of them and it meshes their maps together in order to make one longer one. One of the first techniques that were used in that direction was something called a hypergraph product. A hypergraph product code is a code that very much takes two small classical codes and meshes them together until it has a longer code. But since then, there has been a proliferation of techniques that take short complexes and make longer complexes. And I'll go through an example here. So pick a few small binary maps. Let's call them F, G, H, and I. And these are nothing more than length 2 chain complexes. These are short chain complexes. These are convenient short chain complexes. They're independent. They cannot be used together. It's not like F would be the X checks and G would be the Z checks. They're not obeying the property of being a long chain complex. They're just a bunch of independent short chain complexes. Pick a black box that takes a few short chain complexes and it produces a longer chain complex. The causal complex happens to be some ridiculously standard, well-known such black box. I don't know why mathematicians use it. Speaking to a few friends in the math department, they told me that it's just a happenstance that it happens to be useful for us. But a ton of constructions that were discovered over the last few years end up being nothing more than a special case of the causal complex. And again, I don't know how the causal complex works. I don't care how it works. All that it does is that it takes independent short chain complexes and creates one long chain complex. And you take those random binary maps, you put them in the causal complex, and you get candidate codes, and then you test them. And by randomly searching for F, G, H, and I, and putting them in here, you at some point, you're basically randomly sampling for good codes, because this method of random sampling basically randomly generates long chain complexes. And that's it. That's all there is to the field of discovering good QLDPC codes. Obviously, that's not true, but that's the spirit of it. A lot of the work is in terms of finding black boxes that have interesting, useful mathematical properties where you can immediately prove something about the discovered code. But you can just approach this as a brute force exercise as well. We couldn't do this in the brute force fashion of just picking a random good classical code and getting the corresponding X code. But with a chain complex, we can do that now. And that's why people like this structure, because it naturally leads to good codes. I guess one quick thing. There are a couple of very standard ways to pick F, G, H, and I. You frequently will see that these binary maps that you start with, they're described in terms of not a small binary matrix, but in terms of a polynomial. I don't have a deep understanding for why this language is used so much. I don't know whether there is a deep understanding to it, but there is a very nice correspondence between polynomials and cyclic matrices. Cyclic matrices historically have commonly been used to as a small binary map to build a bigger error-correcting code. So maybe there are other approaches too, but this is historically a very common approach. You can think of it as writing down a binary matrix requires a lot of data, a lot of space. Encoding it in a more elegant, small way is nice. So instead of people moving around binary matrices, they move around polynomials that represent those binary matrices in a much more compact fashion. So S is this polynomial ring that has a few special properties. This notation, it's kind of long. The proper name for this notation is that we have the quotient ring out of a polynomial ring in an ideal. I don't care too much about those specific terms, but let's just run through it and describe what this means. This F2 of Wxyz means that we'll be talking about polynomials of Wxyz for which the coefficients are binary coefficients, F2 being the binary field. And this quotient here means that W to the power of L would be equal to 1, X to the power of M would be equal to 1, Y to the power of P would be equal to 1, and Z to the power of R would be equal to 1. So we're picking polynomials that have this weird property that if they get to a too high of a power, they wrap around and start being equal to 1 again. So these are polynomials that are restricted to not be above a certain power, and multiplication between such polynomials, if a term has higher than that power, it just wraps around. That's what the quotient part of this notation implies. And such a polynomial can be mapped to a circulant matrix. Basically, this type of polynomial is isomorphic to a circulant matrix. And circulant matrices are just a nice compact class of binary matrices that are mostly used to build these bigger chain complexes. So pretty much any QLDPC code these days is something that starts as a bunch of polynomials that are just the compact way to represent a circulant matrix. Really think of them as a more pretty way to write down a circulant matrix. Those circulant matrices are, each one of them is interpreted as a Len2 chain complex, just a single boundary map. They're put through some black box that spits out a longer boundary map, and a longer chain complex with more boundary maps. And those boundary maps are your X and Z parity check matrices. And that's it. There is a lot of properties of these black boxes that are being exploited to prove interesting things about these QLDPC codes. But the basis of the construction is pretty much that. And the only thing you need to know in order to be comfortable reading these papers is that circulant matrices are frequently written down as polynomials just because it's convenient for these people. And chain complexes are nothing more than a way to write down related maps that have this nice property that the product of two consecutive maps is 0, a property you need in order to have the X and Z checks be commuting. I want to stress that this is a very hand-wavy, high-level description. I don't think this description will be enough for you to start working in the field. My hope is that more than anything is that this description is enough for you to not be blocked by seeing weird-sounding vocabulary. Only thing I'm trying to convey here is bring this vocabulary a little bit more closer down to earth. Of course, there is a lot of interesting math to learn, but it's much easier to learn the math when you understand why the vocabulary exists to begin with. That's all. This thing here is called polynomial ring over a binary field. This thing here is called an ideal and encodes the wraparound rule. And this whole thing is called the quotient ring. A fancy word for division that I'm probably mispronouncing. When it's a division of spaces, they say quotient. Quotient? Oh, okay. Sorry, I'm Slavic. English is not my first language. Quotient. Yeah. And it's 10:15. And I don't know, if you feel like it, we can go for another hour, but I don't really have anything to fill another 15 minutes.